My name is Mateusz Pusz, and today we are going to talk about how we can improve our safety with the proper usage of modern C++ libraries. And specifically, we are going to talk about Quantities and Units library that I'm working on for a while now. Why we are going to talk about this? First of all, on the safety term, safety as a feature started to be really important lately. Right? It's not only US government complaining about C++ not being memory safe language, but also about how we provide new products and how people's lives start to depend on the products that we do, right? So I would say that safety is not important, not only important to developers, it's also important to our end users, right? If we make mistake as a developers, it's not only something like blue screen or restart of your cell phone or application will happen, right? Some fatal consequences can be followed by the mistakes that we do as developers. Some time ago, when we were looking for sci-fi videos, some sci-fi movies that were placed in a distant future, a person, a main actor, or whoever was entering the car, and the car autonomously without a driver was driving this person somewhere, right? It was like 2235 of current year, right? And this feature actually starts to be present right now, right? Self-driving cars appear on our roads, and this is not only about cars, because, for example, surgical machines, right? All of these smart healthcare devices, all of this starts to be mainstream and current technology that we depend every single day in different places, in different jobs. And there will be even more machines with safety or even life-critical tasks in the future. That's for sure, that's guaranteed, right? So safety is a major concern in the C++ community in the recent years. Potential improvements are being discussed, handling of low-level fundamental types, right? We would like to have better fundamental types in the language, the one that have, for example, defined behavior on overflow. We would like to improve core language features like initialization, that, for example, every initializes with zeros, right? Björn Strostrup talks about profiles right now that would be able to support that. And also, we try to provide safer, high-level libraries and abstractions of that. One of the examples may be my physical library, but there's plenty more, like safe integer types or safe, basically, numeric types. That is really important to happen. It's important to introduce in our libraries, in our code. And I claim that C++ developers need help right now. With the new trends, with the more and more important life-critical, safety-critical missions that we have to implement in our products, more and more engineers are expected to write such code in their products. And experience in this domain is hard to come by. We can do trainings. We can do trainings to those people, but training by themselves will not solve the issues and mistakes connected to programming, to coding, right? Because some things are hard by itself. It's not about C++ being hard. It's about the subject being hard to manage. And typically, trainings may not be helpful. At least C++ trainings may not be helpful in this domain, right? In our lives, even in daily communication between people, we often do mistakes. We're, for example, talking about physical units. And this is not connected to C++ at all, to any programming language. We just do these mistakes, and I will show you some examples of such mistakes that happened in the industry and our history soon. Also, code handling, the physical quantities for physical computations, is often written not by C++ experts. They're written by engineers that basically, sometimes physicists, right? That just use C++ as their current tool to make the job done. They do not know much about C++. They're not experts in the domain. They are experts in their own subjects of physics or some engineering they want to model with our programming language, and we have to provide as easy to use tools for them to do the job and as easy tools to diagnose the error that may happen during this programming, this logic, right? Actually, physical units libraries, the most important thing, the most important feature of this is to catch errors and to generate nice error messages to our users, so users are able to understand what is wrong and fix it as soon as possible. And hopefully they will see plenty of those errors every single day. It means that this library is useful. If there are no errors, it means that they probably could use just double or any other fundamental type because they don't do mistakes writing those. And I don't believe it is true, it is possible at all. But if you have a developer that can write all of the code from head with double as a presentation type and don't do any mistakes, never, then you don't need this library, right? And when you're talking about affected industries, for this library, people think often about aerospace, autonomous cars, embedded industries, right? Because those are like obvious choices for this product, or physical units library and computations on quantities. However, this is much broader than one would expect. We have manufacturing, maritime industry, military, astronomy, 3D design, robotics. We had great talk about audio from Rolf Michaels on last CPPCon, how he's using the physical units library in his domain, medical devices, national laboratories, scientific institutions, universities, teaching students, right? GUI frameworks, finance even with HFT. All of those industries and even more can benefit from having such a library in their project. So let's talk what are the issues with units by themselves, even aside from programming language. Let's talk about famous and less famous accidents in our history. And let's start with Christopher Columbus. Christopher Columbus on October 12, 1492, unintentionally discovered the sea route from Europe to America, right? He was intending to come to India, but he found America on the way, and he was actually really lucky to find it, because otherwise probably all of them would starve on the water, as I'm going to tell you later on a bit about this, right? The problem that actually was units related here is that Columbus made some mistakes regarding the units being used in his calculations, and this actually was quite fortunate for him. So he has enough food and water to come to America, because he would not make Japan or India if he was trying to go to the initial destination. Vasa, the famous warship, sank in 1628. It sank actually less than a mile into her maiden voyage. So right after it was let's say launched on the water, it just collapsed on one side. It resulted in death of 30 people on board, and archaeologists believe that one of the reasons for this Vasa ship to collapse was that the sides of the boat was of a different thickness, because they had different teams working on different sides of the boat, and it is believed that one of the sides was developed by in Swedish feet, which is like 12 inches right now, and the other one was Amsterdam feet, which is 11 inches right now. So 1 inch of difference between those different feet used by two different teams of workers on two different sides of the boat. And because of it, one of the sides of the boats were heavier than the other one, and because the boat was unstable because of other reasons, it just collapsed on one side and sank. On July 23, 1993, Air Canada Flight 143 ran out of fuel at an altitude of around 12,000 meters. The reason of this is that fuel for the flight had been calculated in pounds instead of kilograms by the ground crew. And basically the plane ran out of fuel and had to emergency land on the near airfield. It might be a funny story, but a British rock band, Black Sabbath, during its Born Again tour in 1983, ordered a replica of Stonehenge as props for the scene. Unfortunately, the manager of this rock band ordered the replicas in incorrect unit. He was thinking about bits, but he ordered in meters. And because of it, the props were much bigger than expected. They were even much bigger than the originals in Stonehenge, and they didn't fit on most of the stages, and none of the stage actually in the world was able to fit all of them at once. And they paid a fortune for that in order to provide this those props for this tour. Another accident connected to airlines, to flights, happened on April 15, 1999. The plane crashed due to miscommunication between the first officer and the pilot. And the first officer had confused 1,500 meters with 1,500 feet and ordered the pilot to do incorrect maneuver. And the pilot did it, and they crashed into land, killing 3 crew on board and 5 people on the ground, unfortunately. Probably one of the most important accidents that happened in our engineering was Mars Climate Orbiter, that in 1999 started the Mars Mars orbit maneuver to enter the orbit, and basically at this point we lost the communication with the space probe. What it turned out is that they were working 2 teams on this project, NASA and Lockheed Martin. NASA was using SI units for its specification, while Lockheed Martin was using United States customary units. And when they tried to communicate through the interfaces, they provided incorrect numbers between each other. And because of it, the spaceship entered the orbit on a wrong altitude over Mars. In February 2001, the crew of the Moon Park College Zoo built an enclosure for the Clarence the tortoise. When they communicated with the original zoo that was lending them the animal, they communicated how big is this animal, and they said you have to build an enclosure, a box, a cage for a turtle of 250 weight. And then they thought that it is 250 pounds instead of kilograms. And basically the tortoise ran away. And in the very first night from the cage, he just totally trusted it and ran away, and they had to look for it next day. In December 2003, the roller coaster in Tokyo, one of the cars derailed because of invalid computations done during upgrading the specification. One of the axles in the cart broke because of it. Another engineering issue was during building the Hohenbrücke bridge between Switzerland and Germany. They wanted to connect 2 different countries over the river, and during construction, it turned out that there was a sign error, and they ended up with half a meter, a bit more than half a meter of difference between levels of the road on both sides of the bridge. I'm going to talk about this in more detail a bit later on. Also, there were some other issues, like, for example, American company sold a shipment of wild rice to a Japanese customer on an incorrect price. On October 12, 2023, The Guardian, the newspaper, basically provided an article where they said that Malawi swelters with temperatures nearly 68 Fahrenheit above average. If you know Fahrenheit, that's quite a lot above the average temperature, right? Unfortunately, it was not the correct value printed here in the title of this article. They made some issues related to temperature points and temperature offsets, and because of it, they ended up with a wrong value. And the proper value here should be 32 Fahrenheit, not 68. And there are also plenty of non-medical dose errors, and those happen on daily basis in different places all over the world. So as you can see, none of that was, maybe besides maybe Mars Climate Orbiter, but nearly none of them were connected with programming, right? With C++ language specifically. It's just that this domain is hard to communicate between different people. Different people tend to understand different things differently, or the same things differently, in this case, and then we end up with accidents that sometimes are funny, sometimes are fatal, depends on the case. So let's look what happens when you add C++ into the equation. So let's see typical production issues. This is one of the projects that I encountered during my career. And as you can see, this project is far from being used in a safe way, right? There's proliferation of double types, plenty of arguments to the functions are written using this type, and it's really easy to reorder arguments, for example, right? Other issues are related to, for example, usage of magic numbers everywhere, right? I even don't know what those exactly mean. I know some of those values. I don't know what was the origin of them, but I don't know all of them. Right now, I would be probably really scared to touch it. And in order to improve conversions and to provide, not repeat ourselves with magic numbers, typically we provide plenty of conversion macros in such projects, right? You will have here degrees to rad, rad to degrees, to knots, to mph, to kph, to kilometer, and so on. Plenty of conversion macros, which are also not that safe and not that fun to use, especially if you encounter that, for example, in the same project, I actually found different definitions of the same macro in different header files. Also, another interesting case is the lack of consistency. This is the same header file. Those functions are written one by another in the same header file in the project. And notice that in the very first functions, you see lat, lon, and lat lon here, right? Lat lon, and then lat lon and longitude, latitude. And again, the same in the inverse order. And as I said, this is the same header file. And even in one header file, those functions are not consistent with each other. And it's not only about latitude and longitude, but also, let's see here, distance, bearing, distance, in incorrect order. And as all of those types are doubles, if you change the order, no one will basically stop you from doing that, right? No one will complain. So those are typical issues we see in production. And it's not only the project I just quoted here is that bad. I'm consulting different code bases all over the world. And some of those things are happening in many different production projects as well, right? You may also try to think if you're using doubles or other fundamental types or similar abstractions in your code base right now. So this is where MP units come into the play, and also where we try to improve the ecosystem by proposing this library for standardization. MP units is C++20 library that provides comparative safety, right? It correctly handles all of the physical quantities, units, and numerical values. It is as fast as using underlying types, I mean like fundamental types, or even faster in some cases. There should be no runtime overhead. You can just gain runtime if possible, and no space overhead, so you don't pay with additional data types, with additional memory needed for for this abstraction. In C++, it may not be that obvious that it may be an issue, but for example, if you look for similar solutions in Java or Python, they pay a lot in performance, both in space and in time, to provide those abstractions. And of course, this library is heavily optimized for great user experience, right? As I said, this library, the most important reason for those libraries to exist is the generation, readability of error messages, right? And the user should be able to understand what the error is and fix the code as soon as possible. So we are trying to improve the readability of, for example, generated types by the library. Also, it should be really easy to use and flexible. By flexible, I mean also easy to extend. And as this is a generic purpose library, it should basically try to attract and cover the requirements of broad industry, right? It is not for niche. It is not only for specific domain, for specific use case. It should be able to cover everything or most of the things that we expect in entire industry for such a library. That's why it should support any unit magnitude, huge, small, or floating point, like for example, conversion between pi and radians, right? So the degrees and radians with the pi factor in between. It should support system of units. It should support system of quantities to introduce additional safety. It should provide affine space abstractions. It should provide nice formatting for text output, so you can provide the text output as you want. It should support scalar, vector, and tensor quantities properly with proper representation types from linear algebra library, some third party probably, because we don't have one in the standard yet. At least I mean the types for it, right? Because we got BLAS-based for C++26, but those are like a bunch of functions, but no types are involved that will provide such interfaces. Also, some people are interested in natural unit systems, which are quite tricky to implement and work with. But this should also be possible with such a library. And as I said, it should be also easy to extend. MP units work with C++20 as the minimum support required. It works with GCC 12, Clang 16, Apple Clang 15, and until now, none of the MSVC compilers can compile this code without crashing. There are still some bugs open, and we are waiting for MSVC to basically mature up and start to support C++20 code correctly. Additionally, on top, if you have better compilers, newer compilers, you can benefit from stud format support instead of FMTLib. You can benefit from C++ modules and some other extensions to API that makes it more user-friendly. And those are C++23 features, but this is opt-in. You don't have to use it. You may still use C++20 with an older interface that is a bit less convenient, but still works for you. So you don't have to use C++23 today in order to use this library. The library is available on GitHub, Conan, and Compiler Explorer. So you can start playing with this and provide feedback or feature requests if something is missing. As I mentioned, we also started the standardization of this library. A few years ago, I provided a paper in 1935 that was providing a discovery of the subject to the committee, and was basically a paper that was introducing the subject for standardization. And only recently, and during the last meeting in Kona, I provided first papers with MP units interfaces to be standardized. We provided 2980, a motivation, scope, and plan for physical quantities in units library. And right now, in the last mailing for Tokyo, that will happen in March, we will provide 45 paper with quantitative units library with a lot of details. This is a long document, and a lot of design discussions will happen based on this document. There are also some associated proposals that has to be discussed, and hopefully will improve the implementation and will make it simpler to implement this library and similar libraries in the future. We want to discuss number concepts in the library, we want to introduce basic fixed string, so you can provide text for non-type parameters at compile time. And also, we would like to improve how we can handle prime numbers in the standard library. So we'd like to have compile time prime numbers facility in the standard. Because actually it's really hard or even impossible to implement this by yourself with the standard facilities we have. So a compiler support may be useful in order to provide this correctly. And it turns out that there is a high interest in standardizing such a library. So not only parties involved, like authors and companies universities are interested, but it seems that also committee members and plenty of people are actually cheering in order to get this into the standard, because this is about safety, and this is about so-called vocabulary types. Vocabulary types are the types that are used as in the interfaces to talk between different vendors, right? Interfaces have to use standardized tools in order for them to be efficient, and so different vendors can communicate between each other. So this is one of the major reasons why we believe it should be a part of the standard. Before I will show you much more examples about how you can code with that library, let's first maybe provide a quick domain introduction to know what we are talking about, because this domain seems to not be that easy as one may think. First of all, we have two different abstractions. We have so-called system of quantities and system of units. System of quantities defines how different quantities, by this I mean some for example dimensions, without talking about units or values at all, how they correlate, how they interact with each other, right? Everyone knows that speed is a length by time. And this is exactly what system of quantities is about. It doesn't say anything about units, it doesn't say anything about representation types. It just says what a quantity is and how it's constructed from other quantities. And then based on such system of quantities, one or more system of units may be created. And we can create like SI system with SI units on top of some system quantities. We can provide CGS or USCS or even natural system units on top of those. Right? So system of quantities is a set of quantities together with a set of non-contradictory equations relating those quantities. And the most important example here is so-called ISQ, International System of Quantities, standardized by ISO. And this is the well-known system of quantities based on the 7 base quantities, right? The one for which SI provides units. So SI is a system of units. It's a set of base units and derived units, together with their multiples, submultiples, so basically prefixes, defined in accordance with given rules for a given system of quantities always. And the primary example here, of course, is an SI, International System of Units, provided by CGPM and based on the ISQ. It's explicitly stated both in SI and in ISQ that SI is based on ISQ. And when we are talking about the domain, we are using different terms like dimension, quantity type, quantity reference, unit, and quantity and a number. And it's good to understand what it means. Dimension basically is a dimension of one of the base quantities in ISQ. Length, mass, time, electric current, thermodynamic temperature, amount of substance, luminous intensity. Those dimensions have assigned letters, identifiers, unique identifiers by ISQ. And this is what we have for dimensions. We can provide the dimensions of derived quantities by just doing arithmetics on those. Right? So for example, force will be denoted not as some other letter of force. Force is always noted as some product of base dimensions or quantities, dimensions of the base quantities to be exact. Right? So LMT minus 2. So there's not such things like a dimension of force, but force may have some derived dimensions, and some derived quantity of force may have a dimension with this equation. Quantity type. Dimension is not enough to describe a quantity. In many places, we need more. For example, we may have different dimensions like length, time, speed, power. This is, of course, what we want to deal with. But sometimes we have the same dimension, but a different kind of a quantity, like work versus torque, frequency versus activity, or bitrate, right? Area versus fuel consumption. They have exactly the same dimension, but mean something fundamentally different, and we don't want to mix them in our equations. The same dimension and kind, but still distinct. Like radius, width, height are totally different quantities of length, and we should not be able to mix them as well if only possible. Or potential energy, kinetic energy, thermodynamic energy, also different, right? You don't want to be able to mix them easily in your project as well. Next, we have quantity references, and the ISQ says that quantity reference is a measurement unit and a few more things that I will mention in a moment. So measurement unit has designated by conventionally assigned name and symbol, and provides an SI unit for all ISQ dimensions. And we may have different units for the same dimension, like joule per Kelvin is a unit of heat capacity and entropy at the same time. But for example, if we talk about 1 per second in terms of frequency, we always should name it Hertz. But when we talk about 1 per second in terms of activity of radionuclides, then we should name this unit becquerel rather than Hertz or 1 per second. Right? So the unit sometimes has different name for different kinds of the quantities, even if the dimension is the same. And besides measurement units, quantity reference may also be a measurement procedure or reference material, but typically we don't care about this too much in C++ projects. Quantity is a number and a reference by the definition. And we have different kinds of numbers we can use. We may have scalars for length, we can have vectors for things like force, or we may have tensors for things like stress. All of this should be somehow supported by the library as well. And the library should provide at least those operations, right? We should have simple numeric operations like division, multiplication by scalars. We should have conversions to common units, so you can do arithmetics on one dimension, or one kind, to be exact. And we may have cross dimensions arithmetic operations. So basically, if you will divide or multiply one quantity, one dimension by another one, you will end up with a quantity of a different dimension or a different quantity kind. Right? So length by time is a speed, and so on. Meter by meter is area. Length by length will give you dimensionless quantity. Right? Or inverse of a quantity will end up in a different quantity. All right, so this was a short introduction to the domain. And let's see how actually Unix library can improve your code, assuming that you are somewhere still in the double length. If you're in the double length, then hopefully you're paying a lot of attention and tracking all of the units you use all the time, right? And this can be done with proper prefixes, postfixes to local variables, like distas m, and provides you information that this is distas in meters and not in some other unit, or that you have speed in miles per hour or speed in miles per second, meters per second, right? And time to goal in seconds. This is quite hard to track because it is really easy to actually make an error here. Also, as you've seen already, I made a mistake. I said this is miles per hour, but it's meter per second, right? Because this is just an abbreviation, and M and M is here the same. So someone may be also confused what it means. But it works. It works if it's tested correctly. It works and provides decent performance. With the so besides those postfixes that specify exactly unit, also we need some conversion macros to convert between different quantities, right? So here convert the miles per hours to meter per seconds using some conversion magic number. If we say that magic numbers are wrong, so then we are providing those preprocessor macros in order to improve what we have. And the preprocessor macros basically can provide you all of the conversions with a unified syntax, so you don't have to write magic numbers anymore. But we say in C++ we should not use preprocessor, so maybe you will say, okay, const factors are better, and of course you may implement this also as const factors. But again, it is quite hard to use, and you may end up with maybe inconsistent definitions in different translation units as well. So let's see the same example with physical units library. We don't need to provide any special names for units anymore. So you just say distance, speed, time to go, and providing the unit right away during construction. Otherwise, you will not be able to construct a unit or a quantity without specifying the unit here. Right? Notice that I also don't have to specify this conversion factor here because the library knows it based on the definitions of the specific units. So if I just divide distance per speed, I can say I want the result in seconds, and I have it in seconds. Right? And I get exactly the same result in both cases. If I make an error during calculation, so instead of division, right, I would have a multiplication, then some strange things may happen. In the regular double use case, we may end up with incorrect value being returned from the arithmetics done here, and this is of course a typical source of issues we have in this domain. In our library, we will get always an error for such errors in logic. Right? We'll have information that if you have distance times speed in seconds, it will tell us that it cannot be converted to seconds, the result of this multiplication, because it has incorrect units. The error we try to provide is to be terse, right? So we have information that we deal here with incorrect units, and that we cannot convert something that's power length per time to seconds. So the derived types are quite easy to read and understand what it means. All right, so we have this non-use library case, and we said we have the same case using strong library like NP units. All right, we provide some calculation here, another one here, and this provides the same outcome. Notice how hard it is to track the unit basically returned by the function. The unit is attached to a function name, not to a variable being returned, right? So it's the user responsibility to provide correct unit here to something that we would try to assign the result of this function. That's why in the function we have information that returns the value in seconds and takes the value in meters and kilometers per hour. In this case, we don't have to deal with that, right? We have quantity of meters, quantity of kilometers per hour, and quantity of seconds. And the user does not have to care about this because this will be correctly returned and handled by the library itself, by the engine, and user will not have to bother about this, just scope on the logic of the program rather than correctness. Talking about the correctness, let's right now change the unit here. Instead of meter, let's use kilometer. Now, the result is different, right? Even though it's treating the argument as meters and provides the conversion factor for meters to kilometers per hour, if you provide incorrect value, this code will compile, will provide incorrect value as an output. With the physical units library, you will get exactly the same output as before, even you provide incorrect or different units than expected, because the conversion, if possible, if safe, will happen implicitly by the library. If it's unsafe, because, for example, it is truncating, then you get a compile time error. Another possibility is that you will replace the order of arguments. And again, you get some value and a compile time error from the library, right? Could not convert speed from quantity with the right unit of kilometers per hour to quantity of meters. Right? Provides the information that speed cannot be assigned to a quantity of meters here. And notice how easy it is to actually understand what a quantity we are dealing here or what is expected. Those types generated by the library are quite easy to follow. This was not the case like 10 years ago on the market when other libraries were introduced this time. We improved a lot through last years in readability of error messages. By we, I don't mean only MP units, but other libraries like Aurora units, for example, also provides really nice error messages, and this starts to be a mainstream in this domain. Now, let's make a mistake in our calculation again. So let's try to do multiplication instead of division. Another incorrect value from the double case, and correct value provided by correct value in the error message, provided by the correct behavior provided by the standard library, the library used for physical units, where we get the multiplication error here, stating that the result of it does not conform to quantity of seconds. And talking about performance, we have those two functions using plain doubles and strong quantities. If you look into the assembly of one, it is just those two operations. If you look to assembly of second one, those are also the same assembly instructions, just the order is inverse here because we are doing conversion after division, not before. This just depends on the logic that was implemented in this function. But exactly those two same instructions are being done, so it's as fast as a double. And in case you're having more conversions like those, the solution provided by the physical units libraries often can be even faster because they do lazy conversions on units. So only in the last step, you will pay for the conversion step if needed in many cases. So this happens actually when you're dealing with generic programming, right? There is no way to provide generic programming with doubles. With doubles, if you would like to provide generic programming, you will not know anything about the unit, about the type, nothing. Here we can say that we expect quantity of length, quantity of speed, and quantity of time being returned from this function, and everything is handled properly. So I can write distance to turn, car speed, and get time to go. I have to turn right after 6.8 seconds, right? If I'm going to Lake Garda with totally different units, kilometers per hour, I will get information that the travel expected time to Garda Lake from my location will be nearly 16 hours. If I want to start in the half marathon distance race, this is the distance in kilometers. This is the pace I expect to run with. If I call this function, I will get compile time error because pace is not a speed, right? In order to fix it, I have to provide the inversion of pace, which is speed, and then everything works fine. And this is my expected half marathon race time for the run. Also, I may use quantity points. So affine space abstractions, saying that the cloud base is 1800 meters and the glider altitude is 1200 meters. And this thermal strength, so how fast I'm moving up in the thermal, is 4.5 meter per second. And again, I can use the same function to get information where I should exit the thermal to not be sucked by the cloud and not see anything, right? So I know that in a bit more than 2 minutes, I will have to go out. Otherwise, I will be inside of the cloud, which is, first of all, illegal, second of all, really dangerous. So this was look and feel of the libraries and how they immediately improve our safety. But let's maybe break it to pieces and let's talk about features separately to say what we actually get from such libraries. So for example, safe unit conversions, right? We have here quantity of 5 kilometers and we want to have it in meters, which is fine and should be done implicitly because kilometers can only be expressed in meters, assuming that there's no overflow on the fundamental type. You can either provide in meters or you can implicitly convert Q1 to Q2 that is expressed in meters. As magnitudes of the source and destination units are known at compile time, the library is able to provide those conversions for you implicitly in such cases. So you don't have to care about it and basically use some magic numbers or remember even about this. Right? For example, kilo prefix has information that is Mach power of 10 to power of 3. And then we have meter, second being the units of length and time. And some symbols, meter, kilometer, to be able to use those units in a more user-friendly way. This is how we encode units in this library. Notice that unit symbols are opt-in and not brought by default in the SINA space because they may easily collide with your user identifiers that you use for something else. That's why they're not the part of the SINA space. They are not brought by default. You have to explicitly opt in for them to use them. Also, we have additional units for a minute hour that are scaled versions of seconds or scaled version of minutes. Or we have international system with international yard and pound units, where we specify that yard is this ratio of meter, and then mile is 1760 yards, defined here. Why we use this Mach feature instead of ratio? And also why you're not using stud ratio, but our own ratio here. It turns out the stud ratio has some limitations. In stud chrono duration, the magnitude of a unit is always expressed as stud ratio. This is not enough for a general purpose physical units library. Stud ratio is implemented in terms of std int max t, which is always 64-bit number on 64-bit platforms. It will not even grow if something bigger will be introduced because of the ABI issues we may have. So it's fixed forever for this precision. And it's impossible to define units with huge or tiny magnitudes using stud ratio. Like electron volt has really tiny, and Dalton even smaller ratio, which is not possible to be expressed with stud ratio. Also, some conversions, for example, radian to degree, require irrational number like pi, and you cannot express pi with stud ratio. That's why we had to use something different, something else. And this is basically improves how we do unit conversions in our library. And second feature is preventing truncation of data. You don't want to accidentally truncate the data and end up with the 0, for example, in your calculation, right? It could be disastrous to the product you try to apply such a truncated value. That's why the library should not allow you to truncate the data implicitly. So if I will do the operation in a different order than before, not from kilometers to meters, but from meters to kilometers, 5 meters in kilometers would be 0 if I would allow it in this place. Right? Also, if I would convert here from 5 to kilo, it would be 0 again. This is dangerous. That's why you get compile time errors. But it's true if you're doing integral types here. Floating point types are considered value preserving, at least for now, until we have better maybe type traits in the standard library. And we are also discussing this right now with the numerics group. So floating points for now are considered value preserving. This is approach similar to what stud chrono duration does. So if you provide floating point number, everything is considered to be fine, and you end up with a floating point number representing the length in kilometers. In case you would have an int in the front here, right? So basically your source entity uses int. You may value cast this to double and then convert to kilometers, and this will work as well. Or you can convert quantity in integers to quantity in doubles, because double is by default, and this will also work. Also, truncating conversion can be explicitly forced from the code. So in case you want to end up with 0, you may do it, but you have to ask for it explicitly. You may use forced in function to end up with this unit and with this value of 0, or do value cast on quantity to force exactly the same operation. Both of them are explicit, easy to find, easy to search in your code base, easy to spot in code reviews. So we assume it is okay to do truncation if you ask explicitly for it. Also, when you try to assign a quantity in floating point number to quantity in integral number, then we get with compile time errors again, right? Because this is considered truncating, and we don't want to truncate the value. Again, you can use value cast, and then you are safe. Well, safe, maybe not safe, but you are saying explicitly that this is what you want, and we are following your orders. So talked about this, all of those features like unique conversions and truncation of data. Let's have some use case. Let's find out how easy it is to use and how easy it is to forget that actually the library does all of the work behind this stage for you when you're dealing with some problem. So let's talk about why Columbus actually thought that he reached India, and for a longer time he was actually sure that that those people should be named as he named them Indians, right? Rather than what they actually should be called, living in North America region. So Columbus was starting from Spain or Portugal, actually from Portugal, and then he reached I think it was Tenerife, where he resupplied the stocks, the sources, the amount of food and water on board, and started the journey west. Before, he was preparing for the mission, and he learned that Abu al-Abbas Abhal ibn Muhabn ibn Katir al-Fargani, aka Al-Farganus, was a medieval Persian geographer. Columbus learned that Al-Farganus estimated degree of latitude to span 56.67 miles. And we assume at this stage that degree of longitude at the equator should be roughly equivalent to the degree of latitude. So with this calculation in mind, Columbus did some initial paperwork, initial estimations for his travel. So what was the mile at this time being used in Europe? The mile in Europe was based on the so-called Roman foot, or also pes. And it was the length of the foot on the statue of Kossuth. This is exactly the official standard for length in Rome. Today it will be 296 millimeters. And then the Roman pace was the length of every other step of a Roman legionary. So it was measured as 5 Roman feet. And then the Roman mile is a total distance of a length where left foot of a Roman legionaries is hitting the ground 1,000 times. And this is basically the mile being used in Europe at this point. But actually what turns out, in Persia, they were using different length unit. They were using other mile, as I'm going to tell you in a moment. Right, so estimated degree, based on the unit of length, was 26.67 miles. As we have Roman foot, defined as 296 millimeters, and we have Roman pace, defined as 5 Roman foot or feet, and we have Roman mile, being 1,000 of Roman paces. And it turns out that actually it is not the mile that Alfraganus meant. He meant Arabic mile. Arabic mile was different, and it's estimated today that it is 2,163 meters. And also we'll compare it to the geographical mile, so the actual mile that we know today, what is the mile of the equator's 1 minute of arc, which is exactly this value of meters. So we have here the degree, being the unit of 60 geographical miles. We have Alfraganus degree, so estimated degree specified as here with the Arabic mile, and Columbus degree, estimated degree with Roman mile. We were writing an error function that has 2 quantities as an input, subtracts them, takes absolute value, and divides by the exact value, and we get the error in percents as an output. So we can print Roman miles in meters, Arabic mile in meters, and we can print the mile error. And it turns out that the mile error here is 31%. So this is the difference between the miles used by the Columbus and Alfraganus, 31% of the difference. Next, we have the equator length based on those different degrees that we mentioned, or lengths of 1 degree, right? Because it's not an angular unit this time, we just want to express the length of 1 degree. So we are calculating how long the equator should be. And actually we end up that the equator, according to Columbus estimations, was 1,600 nautical miles. Alfraganus claimed it is much bigger, but actual length is in between. So it was actually quite good for the Columbus, because instead of having 31% of error, he ended up with 24% of error when we talk about the actual length of the equator. Another issue, another mistake that was done by Columbus is that Columbus thought that the Earth looks differently than it actually looks. In some English versions of the Bible, there was a quote that 6 parts of Earth are habitable and the 7th is covered with water. And this is what Columbus actually believed. So he thought that most of the globe this Earth is land, and only a part of it, small part, is water, which is not the case as we know it today. Right? So Columbus estimated that he has to travel only 68 degrees west from Europe to get to India. or to Japan. This is not the case. The distance from Tenerife to Bahamas is 6,000 kilometers. The distance from Tenerife to Japan is 10,600 nautical miles. Notice I'm still mixing and using different units here, right? And I'm just passing them, all of them, to a common unit when they are printed. So the Columbus thought this is the distance to Japan, and this was the actual distance to Japan. And fortunately, it happened that this was the distance of his travel to Bahamas. So he did a lot of mistakes on the way, when he was actually calculating the expected number of supplies that have to be brought on board. But he was lucky enough that his calculations were nearly matching the actual distance to Bahamas, and he found land because of it. No wonder why Columbus was so happy in the end that actually he reached some land, because they should already be starving slowly on board, right? Because it was like 200 more nautical miles that he actually expected to travel. So this is the short story of Columbus, why he thought he reached India. Based on his calculations, he was there. He reached there just because he was really lucky that something was in the middle of the ocean, namely Bahamas and Americas, rather than just going through a huge sea ocean to Japan. And also, coming back to our C++ language, notice how easy it was to provide all of those calculations. This code is correct by construction. I was just able to scope on the logic of the story, on all of the calculations, and I didn't have to think at all about units. And probably you didn't have to think about them as well, if they are done correctly or not, how they are measured, right? We use Roman miles, Arabic miles, we use kilometers, nautical miles, and other units all the way, and ended up with a proper result in the end, without even thinking about any conversion factors. Imagine that you have to implement the Columbus story with conversion macros and doubles. How much work is it really, and how easy it will be to make all of the mistakes? But okay, let's move forward. Let's move forward and let's talk about next features that are introduced by such libraries. One of this is called, by this term, explicit is not explicit enough. We have explicit constructors in the C++ language, right? And those are considered to be safe. Everyone probably knows that single argument constructors should be explicit because this improves safety. So this was done also for stud chrono duration. So let's see, if you have a structure X with stud vector of chrono milliseconds, I can put vector and place back 42, and this works. And place back calls explicit constructor. So 42 is put to milliseconds in a vector. However, if tomorrow someone will refactor the structure X from milliseconds to microseconds, this code will still compile but will be incorrect from this moment. This is one of the big issues that we have, and this is the source of safety issues that already happened for stud chrono duration, and that's why we try to do better. With MPE's library, if you specify today milliseconds, tomorrow microseconds, if you provide value 42, none of those will compile. In order for this code to compile, we always have to specify a unit. And we specify a unit here as a millisecond. So today it works fine with milliseconds, and tomorrow it will also work fine with milliseconds, because milliseconds can be expressed in microseconds. Because this is the safe direction of conversion. If it was unsafe, so someone will put here something like seconds instead of milliseconds, you will get a compile time error, rather than just code compiling fine, silently, and having an error, right? So quantity construction in MP units always requires both a number and a unit, and this is to provide safety for such cases. If you have homegrown libraries that do similar stuff, consider doing something similar, right? I'm just trying to convince you that besides the obvious features that you probably are aware of in such libraries like unit conversions and maybe truncation, there are some other aspects that you should think about while designing such library for homegrown solutions, for example. It's not that easy to write a correct and safe physical unit library by your own. Let's look into other use cases. We want to get some numerical value to work with legacy function. Legacy is a function that takes the number of seconds as a number. Instead of chrono duration, right? We have this place back 42 seconds. I pass 42 seconds to microseconds, and then I call legacy function count that takes something in seconds. So I have some seconds here, everything looks fine, but we forgot that there's microseconds on the way. Or maybe milliseconds tomorrow, right? This count will provide incorrect values in such cases. But it looks okay. I'm passing seconds here and seconds are expected, so it doesn't look that bad in the code base, and it's hard to find actually that there is an error. And then you have incorrect value. I passed 42 seconds, and this in seconds was much bigger. In order to prevent that, of course, there is a facility in a standard library called duration cast, and you have to always use it before taking a raw value. Then you have a correct value of 42 seconds. But you have to remember about it every single time, right? And it will be safe if you do refactoring later on. With MP units, if you have similar stuff like microseconds here, you pass 42 seconds, then you cannot get the value by itself. You always have to specify a unit you want to get the value in. So you have to always type numerical value in seconds in order to prevent this issue. Just returning count or number or value, it's a really bad idea to do so. So again, if you have something similar in your homegrown solutions, it's considered also requiring a unit for those always in order to make sure you are correct. Let's maybe talk about other from our mistakes, mishaps that we discussed in the very beginning. Do you remember Clarence the tortoise? Right, the tortoise that got a too small enclosure for him after zoo transfer. Let's think how such an enclosure can be built. How can be spec'd by our interfaces. If you're not having any library, you'll write something like this, right? Length in meters, width in meters, height in meters, and provide the constructors for length, width, and height. And then you have something like base in meters squared and by length, and you provide 2, 3, 1. This is unsafe, right? But it turns out that for every other library on the market that we have, physical use library, solution looks like this one. Length, 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 and maybe area is a strong type here as a length time width, right? But the same error may happen. I may unintentionally, accidentally replace the arguments, reorder the arguments, and have the cage in an incorrect direction, right? So nearly none of the libraries on the market can support this properly, and then we may end up with an enclosure for giraffe being horizontal instead of vertical, and this is not fun. An answer to this may be ISQ, so International System of Quantities that we mentioned before. It provides the base dimensions like length, mass, time, and so on. The dimensions are never explicitly defined in the library. But we introduce also something called quantity spec. The measure is not enough to specify all properties of a quantity. More than one quantity may be defined for the same dimension. Maybe quantities of different kinds, like frequency, modulation rate, activity, quantities of the same kind, like length, width, altitude, distance, radius, wavelength, position vector. All of those are similar but different. And we already said that also we have quantities, they may have different characters, scalars, vector, tensors, and some quantities even may be defined as non-negative. ISQ specifies length in such a way. It says there is length as the base of this hierarchy, and then we have all other quantities forming a hierarchy of quantities depending on each other. And this quantity, this tree can be nicely implemented in C++ and provide additional safety for such cases. And we actually ended up with 3 different conversion levels in our library. We have implicit, explicit, and cast. Let's have some simplified tree for our use case. And let's see. Width is not a length. Width is not a height. Those are different quantities. But width is implicitly convertible to length because every width is a length, right? Length is not implicitly convertible to width because not every length will be width because it may be height. So it's not implicitly convertible, but you can explicitly convert from length to width if needed. Height and width are 2 separate quantities, separate different branches. They should not be implicitly or explicitly convertible because this is a cause of typical errors. But still, for some calculations, you may want to force such conversion, and for this we have the cast level to force a conversion from width and height. And of course, if you would like to convert from time to length, there is no way to do so, even with cast, right? Because those are totally different things that have nothing in common. Also, we may talk about this tree. What is the result if you add width and height? If you add width and height, then actually, sorry, width and width. Width and width here, you end up with width, of course. If you add thickness and width, you end up with width. And if you add thickness and height, you end up with length. This is the most logical answer, right? Any width plus any height will give you some length. And users can easily add new quantities to existing hierarchies. It's easy to extend. So you can specify, I have horizontal length being some kind of length, right? And you may have horizontal area that is specialized version of area where the recipe for its horizontal length times width. And then you have all of the rules working here as well, right? Horizontal length is a length. Length is not a horizontal length. Not every length is horizontal length. Horizontal area is an area. Not every area is horizontal area. Length by length is an area. Length by length, not every length by length is a horizontal area. Horizontal length multiplied by width is an area. Horizontal length multiplied by width is a horizontal area because we have an explicit case for this one. And with all of those, you can implement our box in such a way. We're having quantity of horizontal length, width, and height, and constructors of horizontal length, width, and height, and horizontal area being returned here. If you choose to be unsafe, you can, and you can provide those values, but you may also specify that you want to be explicit, and you are saying, I have horizontal length, width, and height, and this will be type safe. If you want to be type safe, you can be type safe, and then if you will reorder those arguments, you will get compile time error. And it's up to the user to decide where you want to be type safe and when you want to be in so-called simple mode, easy mode, if you want to type less, but has lower safety. If I will do that mistake here, I will pass height to horizontal length. I will get a nice error saying that basically there is a mismatch. No conversion from argument height to horizontal length. And then you end up with proper calculations and always having proper enclosure to your animal, giraffe in this case, right? What should be the result of the following equation? 1 Hertz plus 1 becquerel plus 1 bot. Hertz is a unit of frequency, becquerel is a unit of activity, bot is a unit of modulation rate. All the above are quantities of dimension t minus 1. So the same dimension, but different quantities. I asked different libraries on the market. Boost units claimed that it is 2 Hertz, but it's not supported by boost units. So just compared the first two. I thought that maybe always left-hand side is being returned, so I checked the other way around. I also got 2 Hertz. When I asked Nick's Holthaus units library, also one of the major and the best libraries on the market, I ended up with something better, but still discompiled. I ended up with 2 1 per second, right? This is a logical thing to do because it takes the common unit of those two, but it allows such operations. I asked other libraries from other languages, like Pint from Python. I got 3 Hertz. And when I asked GSR 385 from Java, I got a really nice error message. Short one, stating that the method add on quantity frequency in the type comparable frequency is not applicable for the argument of radioactivity. There's a really nice error message and actually correct behavior. These things should not be added because they represent different quantities. We don't want to be able to mix them accidentally. ISO 8000 says explicitly that quantity kind exists. It says that quantities may be grouped together into categories of quantities that are mutually comparable. Mutually comparable quantities are called quantities of the same kind. 2 or more quantities cannot be added or subtracted unless they belong to the same category of mutually comparable quantities. Quantities of the same kind with a given system of quantities have the same quantity dimension, but quantities of the same dimension are not necessarily of the same kind. And it defines many different quantities of, for example, dimension time minus 1, angular velocity, frequency, rotational frequency, angular frequency, damping coefficient, activity, and many more. Those are different quantities. We don't want to mix them in one equation. In order to implement kind, we introduce kind of modifier. It denotes a family of quantities belonging to the same kind. Such quantity represents any quantity from a kind hierarchy tree. Kind can be obtained with getKind. So getKind of width is the same as getKind of height, and actually getKind of width is kind of ISQ length. Quantity of kind of something is implicitly convertible to quantity from S3, to any quantity, right? So, for example, kind of length is convertible to width, because kind of says I am behaving like any quantity of this thing. Quantities of different kinds can't be compared, added, or subtracted. This is mandated by the ISO standard. And those kind of happens and are used in unit definitions. So seconds, meter, gram, all of them has assigned kind of, saying I'm using meters to measure any length. I don't care if it's width or radius, right? Meter is the unit to measure that. Also, some direct units may have those kinds assigned. And this is true, for example, for radian, steradian, hertz, becquerel, where you say exactly that hertz is a quantity, and basically it measures quantity of frequency, and becquerel is being used to measure quantities of activity. And then if you will do this library in MP units, you get a compile time error like this one stating that those quantities basically are not compatible with each other, they have different kinds, and they should not work. And the same rules apply not only to this case, but also to things like radian plus steradian plus 1 bit, or gray plus sievert. All of those are problematic to other libraries as well. Additionally, we have affine space abstractions. Affine space has 2 types of entities, points and vectors. Point is a position specified with coordinate values. A vector is a difference between 2 different points. One can do a limited set of operations in the affine space on points and vectors. right? This basically improves the safety of your code of your products because it limits number of operations and basically leaves only the code that has cells on those abstractions. For example, if you have 2 quantity points or temperatures, or temperature points of 21 Celsius and 21.4 Celsius, you should not be able to add that. This should be compile-time error. And there are a few operations that are invalid in such affine space abstractions. Adding 2 quantity points, subtracting quantity points from a quantity, multiplying, dividing quantity points with a scalar, multiplying quantity points with a quantity, multiplying, dividing 2 quantity points objects with themselves, mixing quantity points of different quantity kinds, mixing quantity points of inconvertible quantities, mixing quantity points of convertible quantities but unrelated origins. All of those are not supported and will improve safety of your products if accidentally you would try to use it. You will get a compile-time error in order to prevent that. So if you go back to our Guardian article that has incorrect average value from Malawi, we can implement the SI system with those quantity points and in mind, right? We provide absolute zero being an absolute point origin or temperature, and we say that 0 of Kelvin is the same as absolute zero, and we use Kelvin, and we use this in Kelvin definition, 0 of Kelvin, right? We specify ice point being this value of millikelvins, and this is the same as 0 of degree Celsius, and we use it in degree Celsius scale. And also we do this for degree Fahrenheit as well. And then if we have max average for quantity points and delta, we can safely do conversions. For example, here for version in Europe, here for version in US. And then compare that it provides correct headings, correct values for specific locations, right? 18 degrees Celsius in European edition, 32 Fahrenheit in US edition for the same article. And here you have both units correctly scaled in both cases. But this time for quantities. Points are more common than you may imagine. People think about points when they think only about temperatures, maybe about time because of stud chrono time point. But actually, they are more common than we can actually imagine. They may be used also for timestamps, for daily mass readouts from the scale. If you are measuring your body wave, probably it should be expressed like this. Altitudes of mountain peaks on the map. Current speed displayed on the car speedometer, right? Or maybe some distance traveled by car also that you can read out from the meter in your car. Today's price of an instrument on the market. Again, it's a point, and you should implement this way. Improving the affine space intuition will allow us to write better and safer software. And with this, we can actually resolve the Hocken-Bricke bridge case and find out how we can implement this to not have the issue of sign error as it was the case during construction of this bridge. The issue is caused by the fact that Germany is using North Sea as a reference for sea level. This is called officially an Amsterdam sea level. But Switzerland is using different sea as a reference one. The difference between that levels is 27 centimeters. And actually, it turns out that the difference of 27 centimeters was known during the construction and basically during the designing of this bridge. So there was nothing surprising there. So what could be the issue? What could go wrong here? It turned out that the difference in height was clearly bigger than 27 centimeters. It turned out that they have sign error. They subtracted 27 centimeters on the bad side of the bridge. They forgot which one is higher, which one is lower. So they ended up actually in the difference of 24 centimeters, doubling the difference between those sea levels. If you're using this with code, you could provide those 2 points. One will be an absolute point origin, and one will be relative to it with 27 centimeters difference. You can define altitudes for one point and another one for Germany and Switzerland. You can specify some expected bridge altitude, and then some additional operations for the nearest landmarks, some deltas from the landmarks when the base of the bridge is basically touching the ground. And with all of the calculations, I will just move forward a bit because we are a bit late on with time. You may end up with proper altitude on both cases, while still maintaining information which point is being used in which system on which side of the river. But the library is not bulletproof. There are still some safety pitfalls that exist and that could be improved if we had additional features in the language. One of the pitfalls may be this one. If you see this result, what you expect? 5 hours divided by 120 minutes. What would you expect? Maybe you would expect 2.5. But it is not the case. It's not the case because if you have 120 kilometers divided by 2 hours, everyone would assume there's 60 kilometers per hour and there will be no additional conversion being done, right? And if you will have 5 kilometers divided by 24 hours, you will end up with 0 because this is truncating conversion. And this is the reason why when we divide 5 hours by 120 minutes, you will end up with 0 as well. By the way, Modulo works okay. Modulo will provide you proper information. It will just leave 1 hour as the result of this operation. Another issue is the lack of safe numeric types. Integer can overflow on arithmetics. It was actually the cause of Ariel flight crash some time ago. Integers can be truncated during assignment to a narrower type. Floating point types may lose precision during assignment to a narrower type. Right? Conversion from in64 to double may lose precision as well. We really need safe numeric types in the standard library, and we don't have them yet. Hopefully we'll get some in the future, and we'll get also traits that will inform us if conversion between two types is value preserving or not. Also, there might be some surprises during unit composition. If you write something like this, you may expect this to be 30 kilometers per hour, but it is not the case. If you will add a concept here stating is this quantity of speed, you will actually have a comparative error because this is not a quantity of speed. This would be quantity of speed. If you will be dividing by 2 hours, you are dividing by 2 and multiplying by hour because this is how arithmetic works. And it may be surprising to others. It was provided in this library. It was safe initially because initially library required us to do something like that. But plenty of people then complained that this doesn't compile. They wanted to write 60 kilometers per hour without parentheses, and this didn't compile before because the quantity was not able to be divided by a unit. In order to provide this feature, this issue appeared. And there are some other connected issues connected to this problem. But those will surface at some point anyway. If you will be assigning to a strong type or to a concept, you will find out those errors anyway. So all of this will be resulting in comparative errors. So those are not that big issues. At some point, you will get this error anyway. Also, library sometimes allows irrational quantity combinations, and we cannot prevent that, right? Everyone knows that length by length is an area. Width by height may be an area. You can imagine area like this one. But library will also allow something like height by height an area. and we have really no way to prevent such incorrect operations. For humans, it is hard to imagine how we can construct an area from two heights, but the library doesn't care. It's a length, and two lengths is an area, right? There are also some issues connected to handling of quantity of dimension 1. If you divide two ratios of length and two ratios of time, you'll be able to add them, because they are just dimensionless at this point. So even though they mean something different, they can be added and handled like this one. Last but not least are the structural types. In order to structural types, we had to provide members data in quantity and quantity point being public, because this is the requirement of the language. And we want to use those as structural types because we want to be able to pass them as non-typeable parameters, for example, to our relative point of origin that we've seen in the C-levels example. And current language rules require that all members data of the structural types are public. So to summarize, MPU is about safety. It has plenty of features that you would expect, and maybe some of them were actually new to you during this talk, to improve your safety, right? Also, there are plenty of more features that improve your usability and accessibility, maintainability, and productivity as well. So please go and try it. And as we're left out of time, let's move to FAQ section in the Gather Town, and let's discuss this in a moment there. Thank you very much, and see you soon.